In Chapter 6, we looked at ionic bonds, which stole electrons in order to make cations and anions. In Chapter 7, we're going to look at sharing electrons in order to make covalent bonds between two nonmetal elements. We're going to learn how to name those simple covalent molecules and how to draw Lewis structures for both atoms and molecules. We'll see what shape those molecules take and learn the difference between single, double, and triple bonds. Once we know the shape of the molecule, that helps us to determine the polarity and also the solubility of our molecules. Finally, we'll look at the intermolecular forces, the forces that hold the molecules together to make either a solid, a liquid, or a gas, which will help us to determine the boiling point of those molecules. Covalent molecules form between nonmetal atoms and they contain covalent bonds. The covalent bonds are formed when electrons are shared between two different atoms in order for each of the atoms to form or have 8 electrons like the noble gases. The nonmetals on the periodic table are the ones that form covalent molecules. These are the ones that are highlighted in blue. The only exception is when we have a molecule that contains hydrogen and an atom from group 7 on the periodic table. These behave more like ionic compounds. Any other combination of nonmetals will be a covalent molecule. The key difference between ionic and covalent is that covalent molecules are made of nonmetals and they do not have any specific ratio to determine their formulas. So we can have differing amounts of subscripts and those become different covalent compounds. They tell us the exact number and type of atoms present. So for example, we have water, which is 2 hydrogen combined with 1 oxygen. If we have 2 hydrogen combined with 2 oxygen, this is what we call hydrogen peroxide. You may have experienced this or used this if you've ever had a small scrape or injury. It's used to clean out wounds and bubbles and fizzes. We also can have carbon, 1 carbon and 1 oxygen combined to form carbon monoxide, or carbon and 2 oxygens in order to form carbon dioxide. These molecules have very different properties from each other. Oxygen, O2, is the air that we breathe. O3 is ozone, which helps protect us from ultraviolet rays. So their covalent molecules can have different subscripts representing different types of molecules. They are not reduced to the lowest terms, as we saw with the ionic compounds. When we're naming our covalent molecules, we're going to look specifically at binary covalent molecules. Binary covalent molecules means that they contain 2 elements that are nonmetals. We're also, in a future chapter, going to look at hydrocarbons. These are also covalent molecules, but they contain, just as the name suggests, hydrogen with carbon, and they only contain hydrogen and carbon. We will look at naming these molecules in Chapter 8. When we're naming our binary covalent molecules, we're going to start by naming the most metallic element. That means the furthest left or down on the periodic table, the one that is closest to the metals. And we name that by using simply the name of the element. The second element, the least metallic element, is going to be named using the base name, but we change the ending to IDE. The number of each element is indicated by using a prefix that describes the number. Prefix is used in every case except for when there is only one of the first element in the name. In this case, the mono, which is the prefix for one, is left off. If the prefix ends in an O and the element starts with O, one of the O's is dropped. So it would be monoxide instead of monoxide. The prefixes that we use are similar to the prefixes that you see for geometric shapes. So 1 is mono, 2 is di, which we don't typically see with geometric shapes. But after that, 3 is tri, like a triangle, 4 is tetra, like a tetrahedral, 5 is penta, like a pentagon, 6 is hexa, 7 hepta, octa, nona, and deca. Let's try a couple of examples. So sulfur, because there's only one S in our formula, we do not include the prefix mono. So this becomes sulfur. There are 2 of the oxygen, so it's di, and the ending gets changed to IDE, so oxygen becomes oxide. So SO2 would be sulfur dioxide. P, there are 4 phosphorus, so 4, our prefix is tetra, becomes tetra phosphorus. There are 3 of the S, which is sulfur, so it becomes trisulfide, changing the ending to IDE. Try the other 4 examples on your own. Pause the video to try to name them. Number 3 becomes oxygen. There's only one, so we don't include the mono. 2 is difluoride. So OF2 would be oxygen difluoride. N2O would be dinitrogen monoxide. We do include the mono. We drop one of the O's and change the ending to IDE. So dinitrogen monoxide. Cl2O7 would be dichlorine. Hepta oxide. SF6 becomes sulfur hexafluoride. Sulfur hexafluoride is it's a fun gas. It is much more dense than air. And so if you've ever seen somebody inhale helium, which is less dense than air, makes your voice go up. Sulfur hexafluoride, if you inhale that, it makes your voice go down. How about writing the formulas from the names? So carbon starts with C, disulfide is S2. Pause the video and try the other 3 on your own. Boron is B. There's only one of them because there's no prefix. Bromide, tri tells us that there's 3. So boron tribromide is B, Br3. Dinitrogen, N2. Pentoxide, O5. Pent means 5. Di means that there's 2. N2O5. Silicon tetrachloride. So there's no prefix. That means there's only one silicon. Tetrachloride means that we have 4 chlorine atoms.